In this lecture, we'll learn about biodegradable polymers. What is the emphasis on polymers is because the metallic alloys or the ceramic alloys, sometimes they have some certain limitations. Like metallic alloys, sometimes they have much more problems with in terms of their corrosion products. As well, ceramics, they tend to be highly brittle. So sometimes a polymer is needed, which can suffice a temporary assistance to a certain activity, and then it can degrade with time. The problem with the metals and ceramics is that ceramics, they tend to be highly stable. They are bio-inert in nature, and then they tend to be there for longevity, for very high. Their lives are very longer, so they tend to remain in the body for a very long duration of time, and they can't just get degraded. Similarly, for metals, metals, they pose a high risk of being able to introduce certain toxins, or they can also cause some irritations once they are inside the body. So, and to take a particular temporary task of serving as a scaffold or probably providing a sort of a drug delivery, metals may not really be suitable materials, because they have certain reactivity with the blood plasma, as well as they can cause certain undesirable effects in the body. So sometimes it becomes essential to utilize polymers and make them serve a certain purpose once they are inside the body. And in this particular lecture, we learn about the biodegradable polymers. Biodegradable, it means that the polymer has to degrade within certain biological environment. And so that is the overall key of this particular lecture, that we are talking about polymers. So polymers, how they are different in terms of their properties and mechanisms and the processing and all such things. And the polymers tend to be different from ceramics and metals, and they can be easily degraded within the body in the biological conditions. So that is the reason we are talking about this biodegradable polymers. And again, there are certain terms which are associated with the biodegradable polymers. We use certain terms interchangeably, such as biodegradation, bioerosion, bioabsorption, or bioresorption. The common thing between all those four terms is the term bio. And exactly the term bio itself has not really been well established in terms of what it exactly means. And again, it has some general applicability, some accepted definitions, but still it is not well accepted by all the people in the this biomedical or the biological community. So this bio term is still very defined, still very vaguely. But overall, it means some biological system may be comprising of plasma or certain cells or enzymes that can incorporate this particular biological environment. But this terminology is also very important, because that is what will define whether it's a biodegradation, whether it's a bioerosion, or bioabsorption, or a bioresorption. So how these terminologies are different from each other, we'll discuss it a little bit as we go along. But these all again concentrate and hover around the polymers only, because in this particular lecture we'll be talking about the biodegradation of polymers. And these biodegradation polymers help us, because once a person has undergone certain injury or some weakening of a part, then a temporary support is required for certain duration of time. So to support that, we have to implant a particular polymer. And why we are stressing more on the biodegradation part is because if the polymer is biodegradable, we don't require another surgery for removal of this particular polymer. So that is a key feature of the biodegradation part. And because if we try to implant a ceramic or tend to implant a metal might serve as a strengthening or basically the workhorse for a particular support, as a support material. But polymer can also provide a temporary support, and the temporary support can degrade as soon as the weakening part is strengthening with time. So there is a degradation of polymer in harmony with the surrounding material or the surrounding tissue, which is now growing up and taking its own functionality. So for the certain duration of time when the functionality of a part is lost, that part is now being supplemented by the polymeric region, which now degrades with time. So in this particular process, we don't require another surgery, so that we don't require the removal of a particular implant, biological implant, which is again a polymer based. Other than that, we can also have some sort of a dual functionality or multifunctional system, and that can also be made using polymers. And how do we do it? I'll talk about in the upcoming slides. So first thing is the degradable polymer. degradable polymers, it means the polymer is getting degraded. And this degradation is not really biodegradation in this particular term. Degradation means only the short term temporary support, because after it has served its purpose, it can just degrade. And again, so because of that, we don't require its surgical removal. So we don't require the removal of it of the particular polymer using surgery. But the importance of this degradable polymer is that it avoids the long-term safety requirement, because if an implant has to stay inside the body for a certain duration, it has to conform to certain biological requirements such as stability. The part should be stable enough that it can support its function for a stipulated duration of time. It should have enough strength, again, to give out the functionality, to serve the functionality without getting itself collapsed. So it needs to have particular strength in terms of being able to support the load. So that is a term in terms of strength. Stability also comes in terms of being stable. It means it should not get oxidized, it should not get corroded. So it remains in its own pristine condition even while it is induced or implanted into the body. At the same time, it should not also get corroded or worn so easily, because there are some certain moving parts inside the body. So if you make them as a acetabular cup lining, then this part will undergo certain erosion or corrosion, certain wear with the adjoining material, and in the process it will start getting abraded. So we need the particular material also need to be wear resistant. So so all those particular criteria in terms of its stability, mechanical stability, chemical stability, compositional stability, in terms of strength, again it can be fatigue strength, it can be yield strength, so and again it can be mechanical strength, so to support particular yielding behavior. Also in terms of wear strength, fatigue strength, all those criteria can be just negated. Why? Because the material has to degrade. So obviously as the material is getting degraded, it can basically be replaced by the tissues or the on-growing tissues which are healthy. So in those terms, it can avoid the long-term safety requirements once we have degradable polymer. So degradable in this particular terminology, it is just the degradation. The bio term is not really induced into it right now, and it can provide short-term temporary support, serving as a scaffold and temporary scaffold, and then it can basically degrade as soon as the healthy tissues start growing. And above that, the surgical removal does not become necessary, because again the polymer will degrade inside the body and it will be basically excreted throughout certain phenomena, and again it avoids the long-term safety requirement. So it can avoid the stability, strength, wear resistance, corrosion resistance, oxidation resistance. All those terms can be basically negated once you have a degradable polymer. Now coming to the specific terms of what we talked about, the such as biodegradation, bioerosion, bioabsorption, bioresorption. So first coming on to the biodegradation part, in this case we have certain biological agent which can be an enzyme or which can be a microbe, and that particular microbe or enzyme is responsible for the degradation. So in this case we have a long polymer chain, and that thing is now being broken into small pieces by certain enzyme, so that now this particular short chain of polymer, it can now get dissolved or degraded. So when it is dissolved or degraded, it can basically go out in smaller chains, and then it is nothing but the degradation of the polymer. So by biodegradation, we are involving certain microbes or enzymes that those basically break down the backbone or the long chain polymer and then fragments into smaller regimes. And now these smaller regimes become much more easier to get dissolved or deposited or degraded into the body. And again in certain conversions such as from polylactic acid to lactic acid is not biodegradation, because that is caused by the hydrolytic cleavage of the polymer, and this all is occurring without any enzymic activity. So this certain conversion, though they appear to be degradation, those are not biodegradation. So in this particular case we have polylactic acid that is converting to lactic acid by the hydrolytic cleavage. So in this particular process, the polymer backbone is now getting fragmented, but all this is happening without enzymic activity. So only this our hydrolytic cleavage is occurring in this particular case. So from that we are getting this particular degradation, and that is how the dissolution of this particular PLA occurs into lactic acid, and that gets degraded, and that is not a biodegradation, that is only a degradation, polymer degradation. So we require the presence of an enzyme or microbe which is causing the degradation to call it a biodegradation. So that is the overall process of biodegradation, that in the particular biological environment we have presence of either microbes or enzymes to cause a particular fragmentation of a backbone polymer chain into smaller fragments which can now get dissolved or degraded. That is called the biodegradation. Now, the second term called bioerosion. So in this particular case, we have water insoluble polymers, and now they are converted to the water soluble components, and this all is happening again under certain physiological conditions. So bioerosion means we have degradation of a polymer occurring within certain physiological conditions. So that is what is happening, that we incur both physical process which cause the dissolution, and again the chemical process which causes the cleavage of the backbone chain of the polymer. So we are making water insoluble polymers, a longer chain of polymers which was earlier insoluble in water, that gets fragmented into smaller chain particles which is again water soluble in nature. So we have two phenomena which are occurring: physical process which causes the dissolution, and chemical process which causes the cleavage of the backbone chain of the polymer. So this all phenomena is occurring under physiological conditions, and this is not by the high temperature or acidic or basic media or even UV light or weather conditions. So this erosion is occurring under certain physiological conditions. There is certain physiological forces which are acting, and that is causing the degradation, and not by temperature or UV light or certain chemicals which are acidic or basic media or even the weather conditions. So bioerosion is basically certain physiomechanical phenomena. So it is called physiological phenomena, physiological conditions assisted by a certain chemical process which cause the backbone cleavage. So that is what is happening, and not because of either high temperature or acidic or basic media, or even by fragmentation from the UV light or the ultraviolet light, or even the weather condition which can degrade the polymer and not cause the bioerosion. So in the bioerosion we have physiological conditions which are dominating, and that causes the insoluble polymer, water insoluble molecule, to get converted into the water soluble molecule, and that erosion under the physiological conditions is called a bioerosion process. So that is again a terminology what we have learned. So we did see that, however, biodegradation is different from the bioerosion, and now we come on to the part of bioresorption. So we do see that our how these particular terminologies are different. So in the bioresorption or bioabsorption, they generally are used interchangeably. So there is not much difference in the biological community to distinguish these two terms, bioresorption and bioabsorption. They are basically used interchangeably. In this case, we have polymer or components which are degraded by cellular activity. So there are certain cells which can basically degrade the material under certain biological environment. So in this particular case, we can give an example of phagocytosis that can occur under the presence of certain cellular activity and under biological environment, and that is causing the degradation of a polymer. So we have certain cellular activity which is degrading a polymer to cause bioresorption or bioabsorption, and since these are all fragmented, they can again get absorbed by the body, or they can also get dissolved into the body, and that basically is causing the absorption or the bioresorption of a particular polymer. And there is no clear definition as yet available what really exactly it means. It just means that under certain biological environment, certain cells, certain cellular activity such as phagocytosis might occur, that is degrading the polymer, and that what is causing the bioresorption. So we do see that there are four terms: biodegradation, again that bioerosion, and bioresorption or the bioabsorption, and we do see that how differently they are being cited. So that is what is happening in terms of all the four examples. And now coming on to the once we have learnt about the degradation of a polymer, how these biodegradable polymers, how they are useful and what are their applications, we can see them. And again we can also stress that there is the biodegradable polymers are again very essential, because it eliminates the long-term safety requirements which might be essential for a long-term implant which is implanted into the body, and also it can avoid the surgery part. like once we have inserted the implant into the body, we don't require one more surgery just to remove the particular implant. That is what might be required for a implanted ceramic or a implanted metal. In case any injury is happening, such as it might happen that a metallic implant gets broken off in the body, so it might require one more surgery to remove the particular metallic implant and then perform the overall repair and then do a repair surgery. But again, in this particular case, we are using the polymer only as a support entity, as a temporary barrier. So that's why in this particular case, we can eliminate the surgery part, because anyway, even when the polymer is left into the body, automatically the healthy tissues will start taking its place and will start maintaining the degradation of polymer, and in the long run, we don't even require the surgery to remove the polymer. It will automatically get dissolved into the body. And coming back to certain examples of it, sutures, they are the earliest synthetic degradable polymers. So those have been utilized for very, very long. Even in the medieval days, when we had all the fights and wars, and all the cuts basically were sutured. So we did had sutures quite long back, and initially the straws were utilized for the sutures. But right now we have certain synthetic degradable polymers which are available to us. So those are basically utilized in this particular case, and we can also utilize them for orthopedic fixation. So we sometimes require some certain temporary scaffolds, which should possess very high stiffness and good mechanical strength. So we require certain temporary scaffolds. Those can be provided by the degradable polymers. So we have sutures which can be synthetic degradable polymers. We can also utilize them in orthopedic fixation for serving as a temporary scaffold, as well providing high strength, high stiffness and mechanical strength, so that they can basically temporarily hold a particular structure and provide and do not deter the functionality of a particular part. They can also be utilized for the drug delivery, and for the drug delivery, the polymer needs to get degraded so that it can temporarily provide breaking of the polymer and release a drug. So we have a particular polymer, it can start degrading, and the polymer can have certain absorbed drug in it, and once the drug is absorbed and the polymer is degrading, automatically there is a release of drug into the body and into the particular targeted area, and that can also be provided by the biodegradable polymers. As well, certain vascular grafts and stents, and in certain cases blood compatibility is also very required, because the blood is continuously flowing in those particular areas. In vascular grafts, you have the clogging or the clotting of the blood might happen. So to avoid the clotting in the undesirable parts, into adjoining parts, if you want to avoid the clotting of the blood, so that the two interfaces are not joined to each other, or in the stents where we have a continuous blood flow, in those certain cases of the blood compatibility can also become a critical issue, because that is again very, very challenging. Because if you have the rupture of a blood vessel and the blood starts coming out of it, it might start clotting, and then it can again just cause the joining of the two nearby arteries, or and then that might be very, very harmful, because it might cause pain for the later surgeries. So that might become a critical issue. So blood compatibility also is a challenge which needs to be undertaken by the biodegradable polymers. And in certain cases, we also require non-adhesion. Like we want some areas to serve as a barrier, because because certain areas when the blood clotting starts, we need to provide certain barrier which will not allow the adhesion of the two interfaces. So we can provide certain soft membranes which will prevent the adhesion. So if you have rupture from one artery, and then we need to provide certain barrier layer, and that will stop the adjoining of these two arteries by this barrier layer. So we also need to have certain barrier layers, and those will not allow the joining of the two nearby arteries or two nearby parts. Otherwise, if they start joining, then it can cause pain later on, because these are undesirable parts which should not really get joined together, and then later on to separate these parts out from each other, again a surgery might be required, and during a surgery it might cause even very high pain. So we need certain barriers as well, which can again come out from the biodegradable polymers. So we can see the overall applicability of these biodegradable polymers. We can start using them from sutures. So those have been used since very long, and then we have certain degradable polymers available with us. and then it can also be for the orthopedic fixation to provide enough strength, as well as stiffness to take care of the initial temporary task of or the temporary functionality in terms of providing support. It can also be drug delivery, because certain regimes, they apart from the support, they also require some chemicals to be induced in those particular regimes. So that can come from the degradation of polymer itself, and during the degradation of polymer, it can also release certain drugs. Again, certain blood compatibility, once we have blood compatibility is an issue, such as in vascular grafts or stents. Again, we can supply certain biodegradable polymers as a support layer, or which will stop the flow of the blood or the clogging of the blood from that particular regime. It can also serve as a barrier layer to cause non-adhesion between the two surfaces. So it can be a soft membrane which can basically separate out the two layers, and it can act as a barrier for adhesion prevention. So these are the certain functionalities which can come out of the biodegradable polymers. In certain cases, temporary scaffolds are also required, which basically are sufficed by the biodegradable polymers. And when a person undergoes certain surgery, or a person incurs certain injury, or during a disease, when normal functionality of a particular tissue is basically hampered, then we need its support so that a normal functionality can be restored during the time of injury, during the time of disease, or after surgery, so that proper functionality can be restored to a person for a better level of comfort. So in that particular cases, we require certain polymers for which can be basically degraded with time. So as we learned that we require certain biodegradable polymers or bioabsorbable polymers or bioerodible polymers that can provide temporary support. So that thing basically is required when we have a weakening of the natural tissue, which can occur basically because of disease, injury, or surgery. So the primary scaffold which can be utilized, which are temporary in nature, it can be sutures, and those are basically required for wounds. So even during time when we get certain cuts, or during wars when people were basically injured a lot, and there was a cut, there was some surface open surface that needs to be stitched together. So we basically have sutures for healing of the wounds, because there might be excessive blood loss once a person has certain cuts. So to avoid that extreme blood loss, we need to provide the closing of the top surface, that is epicutula, the skin epidermis, so that we can provide support, or we can restrict the blood flow from the cut. So we have we provide them as threads, and those threads are basically sutured over the wound surface to provide a support. So in that particular case, we have the surfaces which are basically cut. So we can provide sutures which can basically come, the stitching which can come via stitching of the two areas, and then we have the stitch regime. So we have skin on this side, skin on this side, and this thing we had skin on here, and this was the cut portion. And now after stitching, the two portions have basically been joined together. So that is the way we can apply temporary scaffolds or the temporary support via sutures. The advantage basically out here is the person initially when the sutures were non-biodegradable, then the person had to go again to the surgeon or to the doctor and then get the sutures removed. But in this case, sutures automatically get degraded with time. So there is no necessity for a person to get them removed and go to the doctor again, and they automatically heal with time. So as the healing is occurring, these polymers, they start dissolving into the body, and then these two processes of the dissolution of polymer and the healing of the natural skin, it basically is matched, so that the temporary support can be provided till the person requires it. So till there is a necessity for the support, suture is enough strength to provide the support, and with time it starts getting degraded, and that degradation is now being compensated by the healing of the tissues or the cells around it, and those take care of the normal functionality of the skin. So that is how those two features are now being balanced, and then that is being provided by the sutures. And in case of bone nails, screws and plates, Basically, when a person undergoes certain injury, the bone, if the bone gets broken, it requires a temporary support, because the bone may get the bone might get displaced from each other's interface. So to keep the bone in place and to provide enough support, because in case when there is a huge huge area which is now been broken in the bone, then to fill the gap, certain support is required. Otherwise, there will be a gap between the two areas of the bone, and then it might cause severe pain to the patient. So to avoid that, those particular areas which are now being damaged, or basically which are being removed, those areas are now to be filled by polymers, biodegradable polymers, which can now provide a continuity of the load transfer or the stress transfer from one area surface to the other surface. So we had a bone which is now fragmented in certain regime, and then bone is like this. So to provide a continuity in this particular regime, in this area, we need to fill it with certain biodegradable polymer. So now the bone looks more like this. We have this area, and then we have certain polymer area, and then again we have the bone continuity. So the stress can transfer gradually from this area to this area, from one end to the second end. Otherwise, there will be a discontinuity at the surface. So we will have very high stress at the surface, and then again high stress at the surface, and that might cause a stress concentration, and then that might cause severe pain to the patient. But since we have this continuity because of this biodegradable polymer, the stresses, they go gradually. So from one surface to another surface, there is a gradual transfer of the stress from one end to the other end, with a polymer interface being there. So we can see that part, that the stress can now become much more uniform across the interface. So going from one surface to the second surface, which is now the broken bone, that part, the stress is getting distributed uniformly, and that is being caused by the polymer temporary scaffold. Again, in certain cases, once to avoid excessive blood loss, there are certain vascular grafts, and those are basically utilized for the damaged blood vessels. So if we have a certain injury, and those injury, because of that injury, we generally have certain vascular grafts, they can be kept near the damaged area, and that prevents the blood loss. And again, these can be again clotted, so that the blood vessels again, they can start getting they start repairing themselves without excessive blood loss, because without letting the blood vessels exposed to the proteins and then get clotted. So vascular grafts can assist it can assist restricting the blood loss by serving as a barrier. So vascular grafts are also very much required in terms of the temporary scaffold, and they can get degraded with time, because they can provide temporary barrier to the damaged blood vessels, and then once the blood vessels have repaired themselves, the vascular graft can basically degrade itself. So this is basically what we can see, that the degradable implants, they can also provide temporary mechanical support. So those are the things, that in case once we have certain bone nails, so to keep the bones in place, so like we have a certain displaced bone, then we can provide a bone nail which can basically keep the bone back in place, and then it will allow enough time so that this particular joint gets aligned properly, and then this automatically, the bone nail will get dissolved into the body itself. And again, similarly, the screws and plates, they can also serve as a temporary scaffold in the broken bone. So overall, we can see that the temporary scaffolds, they serve as a support material in the part where we have weakening of the natural tissue. It can arise because of disease, it can also arise because of injury, or those can also be the post-surgery effects. So those can come from such as sutures. So sutures are nothing but the regimes where we have the stitching of the skin because of a cut or because of any injury. So those particular areas, they can be now sutured together or stitched together, and it can help preventing the blood loss. And it now once the stitches are out there, it has nothing but it has joined the two surfaces, so blood cannot flow freely out from the surface. And with time, as soon as the wound is basically healing or the two interfaces are getting joined together, the suture will start losing its strength, and with time it will start degrading. And by the time it degrades, it is now being replaced by a healthy tissue. So in entire process, we have some sort of a balance between the degradation of polymer and the growth of the healthy tissue. So that is what is happening in the sutures. And again, in the bone nails, it can also be utilized for the alignment of the bone, so providing temporary support, or also filling up the areas where the bone has been lost or fragmented. And now with time, what is happening? That support area is now getting degraded. So if you have a certain injury in the particular bone where the bone area is being lost, and that area is now basically, there is a smooth transfer of the stress from one regime to another regime, because we have certain solid degradable polymer which is sitting in that particular area. And with time, what happens, as soon as the polymer is it starts to degrade, that area is now being filled up by the surrounding bone cells. And once bone cells start taking up its place, there is nothing but the healing of the wound. And again, the entire area, the entire damaged area is now being replaced by the bone. Either it can be the bone nail, it can be the bone screw, it can also be the bone plate, and it is being utilized for the broken bones, and then entire polymer can get degraded, and that is now being replaced by the bone cells. So we get an entirely supporting areas or the scaffold, which basically is assisting us in terms of smoothing the stress flow along the particular bone surface, as well serving as at the same time, it is also serving in terms of providing a smooth, painless duration for the patient. So that is what is happening. And again, in the vascular grafts, it prevents the excessive blood loss, and it basically covers up the damaged blood vessels in terms of supporting or avoiding the excessive blood loss. So these temporary scaffolds serve as a temporary mechanical devices or temporary mechanical support materials to help the patient recover during the time of injury or disease or during the post-surgery effects. So that is what the overall functionality of this temporary scaffolds in terms of sutures, in terms of bone nails, plates or screws, or as well as a vascular graft. So we can see that the successful examples, they include a gradual stress transfer. So basically what happens is that degradable implant, it starts to weaken itself. And so in the process, what happens, initially we had this support, the polymer support between the two bones. So initially we are seeing a smooth stress transfer between region 1 to region 2, and this is nothing but a polymeric support. With time, what happens, this particular polymer, it starts to degrade. So overall, the area which is now being supported, it starts to reduce. So now from a higher area, from a higher cross sectional area, it goes on to a lower cross sectional area. So in the process, now bone has to take little higher stress than what it was taking here. In this case 1, in the case A, we had more load which was being taken care by the polymeric material because of its higher cross sectional area. As soon as it starts degrading, now there is a more newer fresher bone which is now getting incepted here. So in the process, now bone has to start taking more and more load with time, because polymer is now degrading. And entirety, there is a gradual stress transfer. It is not an immediate stress transfer, but it's a gradual stress transfer, because in the process, polymer will start degrading at a certain rate. It won't degrade at once. So in the process, polymer is degrading slowly with time. So slowly with time, as soon as it is degrading, it is now being taken care by the freshly or healthy bone cells, which now start to nucleate or precipitate at the bone and polymer interface. And because of that, now the bone area starts to increase, but the area which was being earlier supported by the polymer, that starts to decrease. So bone has to now take little higher and higher stress, but in a gradual step. So what is happening? Polymer is now rendering stress to the bone in steps, in smaller steps. So in that particular process, we are achieving a gradual stress transfer and not gradient or a severe stress transfer with time. So that is what is happening in terms of polymer. So that is again a very successful thing, that the polymer can degrade with time in a slower fashion, that the bone or the natural tissue starts to heal in a gradual manner. It is not drastic, so there is no sudden stress on the natural bone or the natural cell. It is again very slower and steadier, so that a gradual stress transfer can occur out here. So there is degradable sutures. They have been most successful in the human medicine, because for very long there are certain synthetic sutures which are available, such as polyglycolic acid, and again copolymers of PGA and PLA, which are nothing but the polyglycolic acid and the polylactic acid. They are also called catgut in the normal surgical language. And there are also certain Vickrell sutures which are available. There are also certain polydioxanine or the PDS sutures which are again available. But despite all those things which were basically evolved in 1950s, 1960s during the post-war era, still there are no new sutures which are coming in the market. So that is what is happening, that there are certain synthetic sutures which are available, such as PGA, polyglycolic acid, polylactic acid, PLA, PGA, and a copolymer of those two, which is called Vickrell, or again polydioxanine, PDS. But again, these were developed in 1950s and 1960s. But after that, there had been no competing sutures which are available, which can compete with the already available PLA or PGA. This is also because that developing a new material or the new biodegradable material, it requires a very lengthy process of its approval, because the suture has to be tested in vitro, then in vivo on animals, and then again it requires a proper seal of approval, and it requires a very long duration of time in terms of its approval. And again, there are so much complexity which are associated with assigning a particular biodegradable nature to a polymer. So that's the reason there are not many competing polymers which are available in the market, because it becomes very easier for a distributor or a seller to basically market only PLA or PGA and don't go about approval of the other biodegradable polymers. So there have been certain successful examples such as in case of the gradual stress transfer. So like in bone, we supplied with certain zones of polymers, and then that polymer causes gradual increase in the stress, which is now being borne by the bone, and that is now being replaced. The natural polymer is now being replaced by a natural healthy bone as soon as it starts to degrade. And again, the degradable sutures have been again successful, very successful in the human medicine. And despite their development in the early 1950s, 1960s of polyglycolic acid or the polylactic acid, there have not been many changes in the in their development, because again it is a very time-consuming process, and the approval of being biodegradable and at the same time non-toxic, that generally takes a very long time and requires certain testing, and those testings are very lengthy in terms of years, and so that is generally the overall ideology of using only PLA, PGA even as a synthetic suture material. Apart from temporary scaffolds, there are also certain other applications such as adhesion prevention. So such as in surgical, there can be surgical adhesion, because once surgery is being done, there are certain surfaces which basically are cut and for their surgery. So there can be excessive blood loss, and again the blood can start clotting in the extravascular tissue space. But this particular clotting may not be that good, because the clotting might occur between two surfaces which are not meant to be joined together. So that can basically follow inflammation and fibrosis, and that can again lead to pain or functional impairment. In certain cases, that may not be that may cause severe damage, and it can cause the functional impairment of the organ itself. And again, it is very common. This particular prevention is very much required for such as areas where we have severe blood flow, such as in cardiac region, spinal or tendon surgery. So we have severe blood losses which can really occur in the extravascular tissue space. So to avoid the inflammation and the fibrosis and the joining of the two functional parts, and to reduce the pain, we require non-adhering surfaces. So we require a temporary barrier which can come out from a thin polymeric film or a mesh which is now being placed between the adhesion prone tissues. So that is what is required out of it here, that we provide a thin barrier layer or a non-adhering layer of polymer, or which can polymer film or a mesh, that can be kept between the two adhesion prone tissues. So we have one layer and we have second layer, and then we place basically a polymeric mesh which will not allow the region 1 to join with region 2. So in this particular process, we can just leave this particular layer temporary, which is a temporary barrier, out there itself during the surgery, and then it will automatically degrade with time. What the function it will do is, it won't allow the region 1 to get adhered to the region 2. So the adhesion can be avoided between region 1 and region 2, or the adhesion prone tissues which are 1 and 2. So we can avoid that particular addition between the two by providing a thin polymeric mesh or a film. Apart from that, apart from assisting us in terms of non-adhering surfaces, so this particular process can allow us in terms of reducing the blood loss, or also it will reduce the overall pain or the functional impairment. It won't allow the adhesion between the two tissues. Apart from that, it can also be utilized as a artificial skin, because sometimes when there are certain burns, there is some fire somewhere, and then the person gets severe degree burns, then or burns or lesions, then it can also serve as a artificial skin. So this polymeric film can be applied as a artificial skin, and then that will serve as a temporary functionality of serving as a skin. So the direct contact with the environment can be avoided, and with time this particular polymer starts degrading, and that is being replaced by the natural skin, because the skin also starts healing itself. So overall this particular polymeric film or a mesh can also start serving as a artificial skin, and with time this polymer will start degrading, and that will be basically being covered up by the natural skin. So the adhesion prevention can be this particular adhesion prevention can be taken care by providing certain temporary barriers, and that barrier will reduce the pain or the functional impairment, will avoid the chances of pain and functional impairment, and that can serve very well in the surgeries which are common, where this particular phenomena is common, such as in cardiac, spinal, or the tendon surgery. Because what happens, the blood clotting in the extravascular regimes, it starts joining the two adjoining tissues which are not meant to be joined together. So to avoid that particular joining, we need a non-adhesion layer, which is nothing but a polymeric layer, and that polymeric layer during the surgery it avoids the joining of the two surfaces, and with time it starts degrading itself. So by the time the natural tissues are already healed, there is no more blood flow along those lines. So already the particular part has healed, and with time this polymer also starts degrading, and those organs or the tissues which were apart earlier, they remain apart without getting adhered to each other. So that is the prevention which is being supplied by the polymeric layer. And apart from that, this particular polymeric layer can also serve as a artificial skin. So during any injury or burn, it can also provide as a support or as a temporary protecting layer for the skin, and it can be utilized once a person has incurred certain burns or lesions. So that is what the overall ideology of using the adhesion prevention and serving as temporary barrier for the polymeric materials. And there is one more most widely application of this degradable polymeric material is drug delivery. This is one of the very key functionality of a biodegradable polymer, and this is the most widely investigated application. And because for a drug delivery, the overall device has to be temporary in nature, because once a particular device has delivered the material, its task is basically done. So we do require by the demand of this particular functionality that the polymer has to be degradable, or the device has to be degradable. So this is one of the most widely investigated application, and in this particular case, degradable polymers are the well suited materials, because those can serve as a temporary scaffold or temporary storage store media for a particular drug. And once it has gone to the drug site, once to the targeted site, it can basically degrade and supply the drug, and that's it, and then it can degrade with time. And again, this temporary nature, the degradable nature of polymer now avoids any surgical explantation, because once a polymer has to be induced with certain drug into the body, we require surgery, and had the particular drug delivery device, had it been permanent, then we require one more surgery to explant that particular device. So it is very, very nice if the polymer itself is degradable in nature, so it avoids any surgical explantation. And again, this particular area is again dominated by the PLA or the PGA, polylactic acid or the polyglycolic acid. And what it does, it has a controlled drug release rate. So we have a polymer, and it has a drug absorbed into it, and as soon as with time, it starts releasing the drug in the targeted area, and as soon as it starts degrading, automatically the drug is now being released into the targeted area until it basically collapses completely. Again, there are certain basically materials which are such as intercranial polyanhydride polymers, which can deliver drug basically for brain cancer, which can be chemotherapeutic agents, and they can be utilized for curing glioblastoma multiforme, which is nothing but a form of a brain cancer. So we can utilize this intercranial polyanhydride, which is a particular chemical or a therapeutic agent, and that can be utilized for the curing the brain cancer. So this can be again basically implanted into the PLA PGA, and that can again be sent to the targeted area, and once the drug is released, as soon as the polymer starts to degrade. So this is a very wide applicability of this temporary nature of this particular polymer material, that it starts to degrade and it starts releasing the drug as soon as it is being degraded. So this controlled release rate assists in this particular fashion, that as soon as the polymer is degrading, the concentration of the drug can be controlled. That once it is on the surface, a high drug is now being released. As soon as it starts to degrade, a lower concentration of drug can be released, which is again can be engineered, and that will assist the overall supplying of the drug to a particular targeted area. Because initially, when a person is suffering from a particular cancer, very high doses are required in the start, and to maintain the functionality of that particular part, the drug content is it's basically reduced to a certain extent, and that can be easily controlled by the degradation rate of a particular polymer. So drug delivery is one of the very important components of this component of the degradable polymers, and it can be utilized for utilizing certain drugs, intercranial polyanhydride, for delivering chemotherapeutic agents for curing the brain cancers. So this is basically the functionality of the drug delivery devices. Apart from that, there can be multifunctional devices. This polymer can also serve as a multifunctional components, because it can combine several functionalities, such as in the stent area. Like once we have artery collapse, we can send a biodegradable stent, and that will initially prevent the artery collapse. At the same time, it can provide anti-inflammatory or anti-thrombogenic drug. So it won't allow the thrombosis or the inflammation to occur in the particular area that might arise because of the once there is some foreign body into the area, that can be avoided by the anti-inflammation or the anti-thrombogenic nature can be basically negated by the particular drug, which is now coated onto the stent surface. So we have the stent surface, and then we have the artery, and once this particular stent starts to open up, it has a coated drug onto it. So the stent surface area, this is the artery, this is the overall artery, and then this is the overall stent, and stent is now coated with a particular drug that can prevent that can basically be supplied for the anti-inflammation or the anti-thrombogenic activity in the injured area. So this is the artery area which was injured, and now the stent is now taking its place, and that stent is also covered with certain drug to provide certain anti-thrombogenic or the anti-inflammation of this particular regime. So again, that is one component of it, that multifunctional device. It is serving two folds. First of all, it's servicing as providing a mechanical support, because the stent has to open up, it has to keep the artery from collapsing. So it has to support that particular opening up of the artery. At the same time, it is providing a drug. So it is serving as a multifunctional device. At the same time, such as in ultra high strength polylactic acid, it has to supply certain mechanical strength to the bone or nail screw. At the same time, it has to supply certain site specific drugs. So again, we can see that ultra high strength polylactic acid can also serve as a support material for the scaffold or the bone screw or the bone nail. At the same time, supply certain drugs to it for certain site specific functionality. So we can see that multifunctional components can also basically be served by the degradable polymers. So in entirety, we see that the biodegradation can happen once we have the degradation occurring in presence of certain enzymes or microbes in which is basically causing the degradation. So we have enzymes or microbes which is causing the degradation of the polymer, and that is resulting the biodegradation part. Then we had bioerosion. In that particular case, we had the physiological conditions plus which are basically causing the dissolution, and secondly we had some chemical activity which is breaking the backbone of the chain to cause the dissolution of the particular polymer. So then we had this bioerosion, and then it was followed up by bioabsorption or the bioresorption. In this particular case, we had certain biological environment of either any cellular activity which is degrading the particular polymer. So from that we learned the different classes of the bioabsorbable polymers or bioresorbable polymers or the biodegradable polymers from that particular front. So we had couple of classification in terms of them, but there's no sacrosanct or accepted definition of all these. So this is still in basically discussion or still in being acceptance by all the researchers in biological or the in the biological community. Again, we learnt about the temporary scaffolds, how they are being utilized in terms of providing certain functionality to a broken or an injured part, which can come out from sutures. So sutures serve as a temporary PLA, PGA type polymers, which can apply the stitching on a injured area, or those can also be coming out from the anti-adhesion surfaces. The anti-adhesion surfaces will not allow two nearby parts to join with each other. They can also serve. They can also be provided from the They can also come out from the multifunctionality. They can also be the drug delivery part. So a drug can be delivered by using a certain polymer, and that can degrade with time and provide a particular chemical or drug to a specific site. Those can also be multifunctional in terms of providing drug as well as serving as a mechanical support for a particular regime. So those parts can also come out, and those can also be certain temporary vascular supports. Those can come out from the temporary scaffolds or adhesion prevention, or it can also be the drug delivery and multifunctionality of a particular biodegradable polymer. So we can see how myriad applications biodegradable polymer can have, starting from supporting as a suture or serving as a temporary non-adhering surface, or it can also come out from delivering drugs, or they can also serve as a multifunctional devices for drug delivery as well as certain mechanical support. So that is the overall feel of the biodegradable polymers, and basically I'll end my lecture here. Thanks a lot. Thank you.